Hi folks, welcome back. We're going to look at oxidation reduction or redox reactions for like the next 10 pages, 8, 9, 10, 11 pages. So I'm broken this up into two parts. The other thing is I think these videos are getting pretty big, turning into big files. I'm going to speed up a little bit knowing that you can stop or go back and review things. And of course this is in your book. So there's the other resource. So what I want to do with redox reactions is start off with like, what's the terminology? How do we sort of sort out all these pieces? And then in the end, we'll do a little more practice sort of assessing an entire reaction. So I'm going to jump right in, as I always do. Here's a redox reaction. We'd recognize like, oh yeah, there's an element alone. There's an element alone. Redox. There's a charge thing, there's a charge thing. Over here, I'd say, well, copper's 0. Oh, went up to 1. Silver's 1. Oh, dropped down to 0. So that's that criteria that's the real driver are the charges changing. Now here's this first term, reduced. And I'm going to tell you that it was silver ions. Silver 1 was reduced. Now, without knowing anything else, what happened to silver's charge? Well, it went from 1 down to 0. So you stop the video for a second and think, well, wait a minute. It was up at 1, now it's down to 0. Did it gain or lose electrons? All right, you're back. You know that if the charge went down and electrons are negative, it must have gained an electron or electrons. Now the other process, the term for the other process is oxidation, and I'm going to tell you that copper was oxidized. Now I want you to look, what happened to copper? It went from 0 up to +1. Did it gain or lose electrons? Stop the video and think about that for a minute. Well, if copper's charge went up, it must have lost electrons. Okay, so the term reduced, the term oxidized. Now, these always go hand in hand. One reactant does it to the other. So if silver was reduced, it was reduced by the other thing that was there. It was reduced by copper. And so we say, oh, the reducing agent, the other reactant, is the thing that did this reduction. Well, we said copper was oxidized. Well, the other reactant that was there to do that to copper was silver. Okay. Now, I've summarized this in a table. Here's the key thing, I think. This idea of reduced means that its oxidation number, its charge, was decreased or reduced. I think that's the easiest place to start. Say, oh, well, whoever got reduced, oh, their charge got reduced. Well, if you get reduced, did you gain or lose electrons? You must have gained electrons. Now, if you're gaining electrons and being reduced, you are oxidizing another reactant. So we'll say, well, this is the oxidizing agent. Then oxidize is just all the opposites. If reduced means your charge was reduced, oxidized means your charge must have increased. If your charge increased, you must have lost electrons. And if you're losing electrons to somebody else, you are the reducing agent. Now, that seems kind of messy, but I always argue that, if I can find a good red pen, I always argue that start with this everything else will fall into place if I can figure out which charge was reduced. All right, let's go on to the next page. I'm on page 5.14 then. Now I'm looking for who got reduced. Well, look up here. Copper went from 2 down to 0. Iron started at 0 and went up to 2 plus. So I said, oh, okay, the element reduced, copper 2 plus. What was oxidized was iron. Well, if copper 2 plus got reduced, it must have oxidized the other guy. If iron got oxidized, it must have reduced the other guy. And I always start again. If I start with this, I can figure everything else out. This one's a little more complicated. Who got reduced? Well, let's see. Magnesium here is 0. Chlorine is 0. Chapter 2. Over here, oh, wait a minute. Magnesium, 2 plus. Chlorine, 1 minus. Who got reduced? Chlorine. I'll do it in red. Chlorine got reduced. It went from 0 down to minus 1. Magnesium went from 0 up to 2 plus. Magnesium got oxidized. If chlorine got reduced, it must have oxidized the other guy. And now here's a slight variation. When we say the agent, we mean the whole compound, everything over there. So it was chlorine that got reduced, but the thing that it was in was Cl2. Cl2 is the oxidizing agent. Magnesium, the reducing agent. Down here, again, I might go through and say, well, I know the easy one. Aluminum is 0. Chromium is 0. Oxygen, we know, minus 2, minus 2. So we're looking at chapter 3 again. For this to work out, chromium has to be plus 3. Now, if that doesn't make sense, you might want to stop and go, oh, wait a minute, how's that? How is chromium plus 3? Why is that? What's the charge on a compound? 0. Over here, I know that, oh yeah, aluminum's in that column 3A or 13, that's plus 3. Okay, whose charge was reduced? Chromium. Chromium went from plus 3 down to 0. Aluminum went from 0 up to plus 3. Aluminum. Well, whatever element got reduced is inside the oxidizing agent. So the oxidizing agent must be Cr2O3. Aluminum got oxidized. It must have been the reducing agent. Why don't you try problem 5.9? The answer to that is in the back of your book. So you could try that. And that'll shorten the size of this file a little bit since you've got the answer. Now, this is pretty straightforward when we're talking about ionic compounds. We've done all this in chapter 3. It's going to get a little bit messier because lots of important redox reactions do not involve ionic compounds. So, here's a redox reaction. There are no ions, no ionic compounds, no charges that are changing. So here's what we're going to do. I'll make a note. These are not ionic compounds, not ions. But this is a redox reaction. So here's what we're going to do. We're going to pretend all compounds are ionic. So we're saying, well, every compound, every group of atoms stuck together in a compound, a polyatomic ion, we're going to assign some charges. And these sort of like new pretend charges that aren't real, I'll say, well, let's call them oxidation numbers. Now, oxidation number means a real charge or this new pretend charge. But we use oxidation number. We may even use the word oxidation state for this chapter when we're talking about redox. Well, we're going to have the rules for let's pretend. And it turns out the rules initially are very, very easy. Elements alone, 0. Elements alone, 0. Chapter 2. They're just 0. We didn't look at any charges when we were in chapter 2. Now here I've got an ionic compound, chapter 3. So how do I know calcium's +2? How do I know bromine's -1? Well, those are our sort of monatomic ions that follow all those patterns on the periodic table. So we say, well, the oxidation number equals the ionic charge. So far we haven't had to pretend at all. Elements alone, same number of protons and electrons, they're 0. Atoms that have become ions in ionic compounds, that's easy. We already know those. We know all the patterns. Let's go to page 5.16 where it'll get a little messier. Okay. Now, carbon monoxide, it's molecular, it's covalent. It is not an ionic compound. There are no charges there. But here are my sort of magic, unicorn, rainbow, fairy, pretend oxidation numbers. So here's what we're going to do again. Molecular compounds, pretend ionic, and secondly, who gets to pretend they're an anion? Well, remember chapter 4, electronegativity? That's what we're going to use. More electronegative gets to be the anion. More electronegative. Maybe I better say most. Most electronegative equals the anion. Now that's not true, but it makes the accounting work out pretty nicely. If I look at this next one here, number 5, ch04, I've sort of just assigned that. I'm assuming that carbon is going to be negative. It's more electronegative. But where have we seen H+? Oh, yeah. Chapter 3 and 5, acids. Now, this is not an acid, but it's something we've already seen. So we go, okay, we're going to say hydrogen is always assigned +1 for Chem 51. Now, if that's an ionic compound, the total charge is 0. What does carbon have to be to make that 0? So you might want to stop the video for a second and think, oh, wait, if hydrogen's +1 and there's 4 of them, what would carbon have to be? Well, you spend a couple of minutes scratching your head about that. Carbon must be -4 to make that work. 4 times +1 is +4. -4 gives me totals of 0. Wait, what happened to my... Oh, there we go. Oh, sorry about that. Excuse me. Very, very professional video production. Okay. So hydrogen's always +1. The more electronegative gets to be the anion. So I look at this. Chlorine is more electronegative than silicon. Fluorine, more electronegative. And I remember from chapter 3, like, oh yeah, chlorine's always going to be -1. Fluorine's always going to be -1. What does silicon have to be to make that 0? +4. Fluorine's -1. What does nitrogen have to be to make that 0? +3. Now, if that doesn't make sense, stop the video, think about that. Like, oh, wait, how does that work? Oh, yeah, because the total charge is going to be 0. And then look at these unusual things. Oxygen, hydrogen. We said, oh, for Chem 51, we're always going to assign +1. And we're going to assign the anion to the more electronegative atom. And bingo, if I put one oxygen, one hydrogen together, oh, wow. I know that's what you're saying. OH-. Oh, hydroxide. Okay. So in a polyatomic ion, the sum of all the oxidation numbers has to equal the actual charge on the polyatomic ion. Okay. Hydrogen, we said, oh, that's always going to be +1. Nitrogen is more electronegative from chapter 4, so bingo. 4 plus -3 gives me a total of +1. Now, what about phosphate? Well, oxygen's going to be -2. We don't know what phosphate's going to be. We would have thought maybe -3 in the past, but oxygen's more electronegative. It takes precedence. It gets to be -2. Now the total has to be -3. That's the charge on phosphate. So I've got 4 of these oxides, 1 phosphorus. Total has to be -3. I could do it like this. 4 times -2 plus phosphorus equals -3. I do some algebra there, and I get +5. So here it is. Rule for assigning oxidation numbers. The sum of the oxidation numbers equals the charge on the polyatomic ion. So if I had CO3 2-, there would be my charge. If I had phosphate 3-, if I had nitrate -. So the total of all those oxidation numbers has to equal the total charge. Here I look at these: carbon, nitrogen, nitrogen, carbon. Nitrogen gets to be -3. It's more electronegative. To make that a total of -1, carbon has to be +2. Again, if that doesn't make sense, stop the video, think about that. How does that work? I'll emphasize that's cyanide. Here I've got acetate. Oxygen's the most electronegative. It gets to pretend it's an anion. Hydrogen, we said, well, our rule is going to be that's just +1. What does carbon have to be to make that work? Now you might stop the video and think, okay, I've got 2 carbons plus 3 hydrogens plus 2 oxygens equals -1. Do that algebra, see if you can sort that out. All right, so this looks a little funny, but carbon is 0. The oxidation number on acetate, carbon is 0. Again, if that doesn't make sense, stop the video, sort that out, see if you can get there. Okay. Last page in this introduction to redox reactions, page 5.17. Here are all the rules. Elements alone are 0. There's our oxidation number. Chapter 2. Hydrogen in a compound, well, it's kind of chapter 3, chapter 5. Elements in ionic compounds like sodium, oxide, and so on. There's chapter 3, which says, oh, those are the charges we learned in chapter 3. Elements in covalent compounds, molecular compounds, the more electronegative gets to be the anion. Chapter 4. And the sum of the oxidation numbers in a compound is always 0. Now those polyatomic ions like phosphate and cyanide and hydroxide and perchlorate, the more electronegative atom gets to be the anion, and the total of the oxidation numbers has to equal the ion charge total. Okay, let's apply some of those. Now what I would recommend, I'll do the first one. I'll do the first two. And then what I recommend is you stop the video, try to do C, D, E, and F, and then turn the video back on. Of course, again, no, these are not in your book, so I'm going to do these. Bromine, there's an ionic compound, plus 3. Chapter 3. Here we go. Oh, that's iron carbonate. What's the charge on carbonate? Well, the whole thing's 2 minus. That must be 2 plus. Now, oxidation numbers, here's where we normally put the charge and the number. The charge and the number, like we usually do in math. Previously, we've been putting 2 plus. It's fine. Oxygen over here has to be carbonate. So, oh, well, oxygen is going to be minus 2. I've got 3 of those. I've got carbon there. The only way I can make 3 oxygens and 1 carbon come up to minus 2 or 2 minus must be plus 4. A little messy. And remember, I had to know carbonate from chapter 3. If I didn't know carbonate from chapter 3, I'm already sunk. CO2 is easy. More electronegative gets to be minus 2. To make that work, carbon must be plus 4 to give me a total of 0. Sulfur hexafluoride, fluorine gets to be minus 1. Sulfur then must be what to make it 0? Plus 6. Perchlorate, oxygen gets to be minus 2. What does chlorine have to be? So that 1 chlorine, 4 oxygens give me a total of minus 1. A little bit odd. Chlorine has to be plus 7. Lastly, and similarly down here, oxygen's minus 2. The total charge on chlorate has to be minus 1. Chlorine, in this case, its oxidation number is plus 5. Now you might want to go back and review these, look at them over, follow that. This is pretty important. We need this fundamental terminology and ability to assign oxidation numbers before we can do anything else. All right, take a breather, get a cup of coffee. I will see you at the next video, which will start on page 5.18.